Hi, welcome back to Jedi Lesson Week 7th with Reza Padilla. This is going to be our first problem out of 4. Our problem states, using the Bohr model, determine the ratio of energy of the ninth orbit of an ionized atom with 6 protons in the nucleus, and only a single electron orbiting the nucleus to the energy of the ninth orbit of a hydrogen atom. So I'm going to first start with drawing an image just right here. So this is going to be the ionized atom. Right, and this is going to be the electron. Just right here, it's going to be this little electron. And then this is going to be the ninth orbit. And this is the nucleus, and this is going to be the 6, right here, the 6 protons. Right, and now we're going to have over here the hydrogen atom. This is the, this is the electron. This is going to be the ninth orbit. And it's just going to have 1 proton. Okay, so the ionized atom has 6 protons but only 1 electron, so it is a very hydrogen-like ion. Therefore, the Bohr energy equation applies to it. Okay, so before we get into all of that, let's determining the ratio of energy of the ninth orbit of an ionized atom, we're going to go ahead and start with some variables that we're going to need to know. So first, we're going to need to know what En is, and this is just going to be the total energy of the electron in the ninth orbit, and it represents again the total quantized and mechanical energy of the electron occupying the ninth orbit of a hydrogen-like atom, and the SI unit for this is going to be in joules. So I'm going to go ahead and write that. So it's going to be the total energy of the electron in the ninth orbit. SI unit in joules, or just a J. Perfect. The next thing we're going to need to know is Z, and this is just the atomic number, or a number of protons in the nucleus, okay, of an atom. Okay, so let's go ahead. So it's atomic number, or number of protons in nucleus, and it has no units, so no units. Okay, no SI units for this one. And the next thing we're going to need to know is our N, and this N represents it's a principal quantum number. It represents the integer energy level or orbit index of the electron. Okay, so it's going to be principal quantum number representing electron's orbit. Okay, and this one also has no units. Perfect. And we're gonna also need to know what ENC equals 6 means, and this is just the energy of the ninth orbit of the ion with 6 protons. So it's gonna be energy of the ninth orbit for the ion with 6 protons. And then we're also going to need to know what ENC H is, and this is going to be the energy of the 9th orbit for the hydrogen. Okay, perfect. So this is the variables that we kind of need to know. So I'm just going to also write down some of our given. And two of our given ones are our atomic number of protons. So our Z, we have Z, Z equals 6 for ionized atom. And Z equals 1 for hydrogen. And then we also have N, which is going to be the 9th, right? The 9th. Right? So that's what it's also our given. Perfect. And so for an atom or ion with only one electron, the energy of the 9th orbit is given in this equation. So our first step is going to be the Bohr energy equation, as the problem states we must use. So according to the Bohr model, the energy of an electron in a single electron atom or ion with atomic number Z in the 9th orbit is given by En is equal to negative 218 times 10 to the negative 18th power joules Z2 and 2. Okay, so this is that equation, and the negative sign means that the electron is bound to the nucleus. And what we need is this ratio, N C equals 6, and then En equals H. So we're looking for the energy of the 9th orbit for the ion with 6 protons over the energy of the 9th orbit for hydrogen. So this ratio, this is what we need. Okay, so this is what we need to calculate. So we're going to go ahead and write the energy of the ionized atom. So now that we have this equation, we're going to use it for the ionized atom and for the hydrogen. So let's go ahead and start with the energy of ionized atom. Perfect. So we know that the ion with Z equals 6, so we can just go ahead and write that down. I'm going to use this. So En of Z equals 6. Remember, this is for the ionized atom with 6 protons. That's why Z equals 6. It's going to be equal to negative 218 times 10 to the negative 18 power joules. And that's going to be, remember, Z equals 6. We put this right here. And then we have N2, right? And we know that 6 to the power of 2 equals 36. 6 times 6 equals 36. So we can just simplify that and make it equal to N to the negative 18th power joules equals 36 over N2. Right? Perfect. So now this is going to be the equation for the ionized atom. I'm just going to move this over here. Perfect. Our next step is going to be the energy of the hydrogen. right? And again, this is the same step as we did for the ionized atom. We know that the hydrogen Z equals 1, so we're going to just go ahead and do that. I'm just going to do this in a different color so we're able to distinguish it. So N is equal to negative 2.18 times 10 to the negative 18th power joules, and it's just 1, right? We're 2 and 2. We know that 1 to the power of 2 is just 1 times 1, so it's just going to be 1, right? So it's just going to be, technically you don't have to just simplify since you already know that it's just going to be this, but just to keep it, to simplify it. So this is the energy for the hydrogen atom, right? Okay, so now we can use these two energies right here that we've solved for and find the ratio that the problem requests us to. So that's going to be our fourth step. Find ratio. Okay, so what is it that we were looking for? We were looking for this right here, right? So we are E and C equals 6 for E and H, right? That is the ratio we're looking for. So let's go ahead and fill it in. We have exactly that. So we have the top, joules, and then we also have the bottom part, which is negative 2.18 times 10 to the negative 18 joules, 1 and 2. Perfect. So now we have this ratio set up, right? But now the constant, the joule units, the negative sign, and the n square cancel because both electrons are in the same numbered orbit, right? They're both in the 9th orbit, so we don't have to worry about that. So these cancel out, right? So now our whole ratio is equal to as you're gonna be able to tell right here, it's just gonna be 36 over 1. And what is that equal to? 36, right? So basically it's 36 to 1, right? So it could also be just 36 to 1, just like that. Either or. The energy of the 9th orbit of the ion with 6 protons is 36 times the energy of the same orbit in hydrogen. So more precisely, its energy is 36 times more negative, meaning that the electron is bound 36 times more strongly to the nucleus, right? So perfect. So this is our whole thing. So our step-by-step. So first we identified the general Bohr energy formula, right? So the Bohr model shows that an electron's energy depends directly on the square of the nuclear charge of Z squared. Right here, you see, pulling on it, and inversely on the square of the orbit index, which is n squared on the bottom, right? And then we express the total energy for both individual systems, and to find the rate, we did this because to find a ratio between two physical quantities, we must first set up explicit equations for each system using the specific values for each, right? So for the ionized, Z was 6 for the single electron, and then Z was equal to 1, right? For the hydrogen, right? So then we divided the ionized atom's energy by the hydrogen's atom's energy, and then we just canceled any like terms any common terms, and since both atoms evaluated to the same exact ninth orbit, the quantum number n and the basic constant E of right here negative 2.18 negative 10 to the negative 18th power joules, these all just canceled out, so leaving the ratio as simply as 36/1, right? So it just yields to 36, and so that is our answer, right? It's just 36. Perfect. And this is our total problem. Thank you.